Hello everyone, welcome to this talk from OpenHW Group. Today Jérôme unfortunately couldn't be here. He had some personal issue, so he's recorded his presentation and we will see his talk basically recorded, and then Max and I from OpenHW Group staff, we will answer your question if you have any. I'm Davide Schiavone. I'm from OpenHW Group, a non-for-profit organization that creates open source industrial quality hardware, so CPUs in this case. And Jérôme is actually one of our, Thales actually is one of the members of OpenHW Group, and Jérôme particularly curates the technical working groups, and he works on Thales as interesting the CVA6 CPU, which is a Linux-capable application class RISC-V microprocessor.
Good afternoon. My name is Jérôme Quévremont. I work with Thales, and I am also the co-chair of the technical work group of the OpenHW Group. I am sorry that I cannot join today. The OpenHW staff will be with you after this record to answer your questions live. So today, I will talk about CVA6, an open source RISC-V processor core, and I will give a bit of focus on EU support for RISC-V and open source hardware. Let's start with a short introduction of the Thales Group. We are more than 80,000 people working in 68 countries. The Thales Group invests heavily in innovation to develop state-of-the-art technologies for its products. Our mission at Thales is to develop critical solutions for our customers. We are active in the space, aerospace, defense, transportation, and security sectors. What is RISC-V? RISC-V can be viewed as a credible alternative to proprietary CPU cores, such as ARM, which is the major player in the embedded processor market. ARM comes with high costs and export risks. This was illustrated by the trade war between China and the USA, when Donald Trump tried to ban Huawei from using ARM cores. RISC-V is actually an instruction set. An instruction set is a low-level language that is understood by a processor. Unlike ARM, the access to RISC-V instruction set is free and open. It's supported by a fast-growing community, which more than doubles every year. Based on the RISC-V instruction set, one can build actual implementations of processor cores. Some of them are open source, others are commercial or proprietary. Our aim with RISC-V is to achieve the same success story as Linux adoption. Let's see why Thales invests in RISC-V and open source hardware. RISC-V is a nicely designed instruction set, and one can build efficient cores from it. Also, it can be customized to best fit your application and targeted performance. The software you design is compatible across many implementations thanks to the common instruction set. You can use toolchains like GCC without adaptation. For the security and functional safety needs, if you build or integrate open source implementation of RISC-V cores, you will easily be able to audit the source code and ensure there is no black box inside. Also, with RISC-V and even more with open source cores, you avoid to be tied to a specific vendor. This is nice property when you want to maintain an equipment over decades, like Thales. And finally, Thales and European actors are far more protected against export control restrictions with open source. In the RISC-V domain, Thales belongs to two open communities. RISC-V International is the place where the community specifies the modular and flexible instruction set. After ratifying several extensions, the specification of optional and sometimes domain-specific instruction is ongoing. RISC-V International also hosts special interest groups, such as functional safety. And remember, RISC-V International does not deliver implementations. Our second community is the OpenHW Group, which delivers open source, industry-grade RISC-V compatible cores, their software ecosystem, as well as verification environments and other IP blocks. The selected open source license allows their integration in proprietary design and protects against export risks. What is CVA6? CVA6 is a RISC-V application core. An application core is a processor core that can support rich OSs like Linux. The beginning of the adventure was ARIANE, a core that was designed as a PhD project by Florian Saruba at the ETH Zürich. It was later donated to the OpenHW Group and renamed CV64A6. Then Thales designed the 32-bit version of the core, CV32A6. Both cores share the same source code. Open hardware names can look strange, so let's decode. CV is for Core 5, the generic name of OpenHW Group cores. Then you have the architecture size, 32 or 64. A is for an application core. And finally, 6 is a hint about the core performance. From an academic project, CVA6 has started a career at the OpenHW Group to become an industry-grade CPU core. What do you get with CVA6? First of all, you get a core that is fully compatible with the RISC-V ISA, so you can use standard tools like GCC. This line denotes a mid-range core from a complexity viewpoint. CVA6 embeds L1 caches. Its bus interface is AXI4, a common interface to integrate into system and chips. It also has machine, supervisor, and user privileges, so you can implement many different OSs like Linux. It embeds a few safe and secure features, and it gets the needed memory management and protection features. Finally, it's ready for multi-core and mini-core. For instance, it's supported by the OpenPython framework. CVA6 is a highly configurable core to adapt to its users, application and constraints on integrated circuits that are designed as ASICs and FPGAs. The main parameter that you can configure is the architecture size, 32 or 64 bits. Then you have many other parameters like the L1 cache memory size and organization, the optional floating point support, and so on. It's already a bit late, so I won't detail all parameters. If you want to speed up your application, you can plug a coprocessor and extend CVA6 supported instruction set. With the CVX-IF interface, you can add standard RISC-V extensions if they are not implemented in the core. Or you can add domain-specific custom instructions, for instance, to speed up crypto processing, signal processing, and so on. The CVX-IF interface is an OpenHW specification that is featured in other OpenHW CORE-V cores. The compiler support is seamless if you add RISC-V standard instruction. And if you add proprietary extensions, you will either need to tweak the compiler, or you can go an easier way by designing an API that will hide inline assembly code to address the coprocessor. In addition to the core, hardware designers can find in open hardware repositories design examples that they can use as a starting point for the ASIC or FPGA project. Here you can see a core complex with interrupt and debug controllers as well as a few peripheral controllers. FPGA and ASIC designers most often use proprietary cores that are offered by their technology providers. For instance, with Xilinx FPGA, you can get microBlaze cores. With FPGA from Microchips, you will get MI5 cores. So when a company switches between FPGA vendors, for instance, if they encounter supply shortages, the hardware designer will need to make a deep redesign of its hardware and overlying software architectures. CVA6 has a very distinctive property. It is technology independent, and you target both ASIC and FPGA technologies. So you can have a continuum between various architectures and technology providers. This helps significantly save time and money when you switch from one silicon technology to another. One of the tasks that Thales performs in the CVA6 project is to optimize the core for FPGA targets. We have already more than halved the silicon resources used by the core on FPGA. Next year, we want to further increase its frequency. And remember, one can speed up applications at a given frequency if they implement an adapted coprocessor on the CVXIF interface. With the performance figures you can see on the screen for FPGA and ASIC, I think that CVA6 can be a good alternative to proprietary cores for your design. CVA6 comes with a complete software open source ecosystem. It supports U-boot as a bootloader, OpenSBI, which is a common RISC-V firmware. Also, Linux in 32 and 64-bit are supported thanks to Yocto and Buildroot. FreeRTOS is also supported, so you can guess that many other OSs can be supported by the core too. From the compiler viewpoint, GCC is well supported and LLVM is on the roadmap. CVA6 has various debug capabilities. You can use low-level debug in bare metal with JTAG probes and hardware breakpoints. In a few slides, we'll also demonstrate what I call the high-level debug with a GDB server running in Linux on CVA6. Both low-level and high-level debugs work in Eclipse IDE. On the verification side, the continuous integration environment is in place. It leverages open source components from Google, among others. Several test sequences are being developed, some of them reused from open hardware cores. The next steps represent a significant amount of work to complete the test sequences to reach 100% coverage target, which is needed to integrate CVA6 in production ASICs. Here you can find the links to our repositories for the core for Linux and for the verification environment. Worth to note is that the verification artifacts, including the test sequences, will be available as open source. This is quite unusual if you compare with other open source cores that often do not offer the verification as open source. Open source hardware is adapted for industrial use. The OpenHW Group provides a governance to reach industrial-grade quality. As with open source software, open source hardware allows to share development costs, influence specification, and get recognition. The OpenHW Group has selected the Apache and SolderPad licenses that are appreciated for industrial integration. Entities who use or contribute to open source hardware will also generate value by the ability to customize their application, an increased control over their solution, and an easier path to certification. As for open source software, you can create businesses which deliver commercial add-ons or provide maintenance and support offers. And users will reduce their exposition to supplier risk, export control restriction, or even trade wars. Now let's have a look at the adoption of CVA6. It's already used in the MiG-5 ASIC, which is designed by Hensoldt Cyber. Thales has started developing a secure processor with it, and it is considered in other applications in the Thales group. Several other companies, large enterprises or SMEs, are about to adopt CVA6 in various fields: edge computing, automotive, industry, space, and aerospace. As you heard in the previous presentation, Intel has joined the OpenHW Group. They support CVA6 in the Pathfinder environment. This opens the door to many exciting opportunities. Beyond our technical activity, we are also promoting RISC-V and open source hardware in academic communities in France. We have already organized 2 editions of a student contest using CV32A6 on FPGA. In the first edition, the students were competing to increase the performance of the core. The second edition was about the energy efficiency. And we've just kicked off the third edition focused on cybersecurity. If you want to organize such a competition in your region, you can even reuse our technical kit because it's open source. In this demo, we want to show that CVA6 is already a mature solution. We have implemented CV32A6 as a soft core in Xilinx FPGA. Soft core means that CVA6 has been synthesized in the reprogrammable fabric of the FPGA. The demo uses U-boot bootloader and a Linux image prepared with build root. Linux and GDB server run on the CVA6 core that is implemented on the FPGA. You will see a remote debug sessions in Eclipse IDE running on the host PC. It is connected with CVA6 through the Ethernet cable. This illustrates that CVA6 is ready for software development using standard open source tools. The demo you will see runs on a Xilinx FPGA, and it also works on a microsemi PolarFire FPGA. No doubt that we can also target Intel FPGAs. CVA6 is really techno-independent. Now, I will let my colleague Sébastien Jacques present the demo.
First, I switch on the Genesis 2 board. The bitstream is loading in the FPGA. The yellow LED indicates that the bitstream is loaded. On the hyperterminal, we can see the booting of Linux. The boot-ROM program loads U-boot and OpenSBI from SD card to DDR memory. OpenSBI starts and initializes the system and then runs U-boot. U-boot copies Linux image from SD card to DDR. Once the image is loaded, U-boot verifies its integrity by performing a checksum. Then it decompresses the Linux image and launch kernel boot. Now that the Linux is running, we can, for example, show the CPU information. Here, we can see that the instruction set is a RISC-V 32 bits with IMA extension with a MMU SV32 of the RISC-V standard. Then, with uname command, we can have the system information. We can see that the Linux image is generated with buildroot for RISC-V 32 architecture. Then, to show that the CV32A6 is really an application processor, we install Tetris and we can play. Now I can try top command, which shows processes and CPU resources used. The advantage of having Linux is also to have an Ethernet connection. We can see the Ethernet interface ETH0. However, this interface needs to be configured, so here we assign it an IP address. The target is connected to a host PC via an Ethernet link. To check if the Ethernet link is working, we ping the host PC. Here, we can see that the connection is working. Then, what we want to show is that it is possible to develop and debug a software application on the RISC-V target from the host PC. To do so on the host PC, we launch Eclipse. We create a software application hello. Then we compile the application with Eclipse, and as you can see, the binary is created. And then we transferred the binary to the target via the Ethernet link. Then on the target, we launch the DB server, which allows to connect the host PC to the target for debugging the hello binary. On the host PC, we launch the debug. Once connected, we have access to the disassembler of the hello binary. Here we added a breakpoint to the main function of the application and we launch the execution up till the main function. Then we can go to the disassembler. For example, we can dump this memory address. In this memory area, we have the binary of the application. Then we can go to see the registers value of the CPU. And we can run next step command. You can see that the registers values changed. We redo next step command. On the target, we can see that hello world is displayed. Then we come back to the host PC and we resume the application. On the target, the hello application exits. This demo shows that with RISC-V, we have a fully hardware and software open source solution.
Open source hardware and RISC-V are disruptive techniques that can lower the barriers to design innovative systems and chips, an area where Europe has good assets. To foster European sovereignty and to remain competitive in front of the USA, China, and India, European actors have prepared a roadmap which is published by the European Commission. To implement this roadmap, KDT has already launched 2 calls to build open source RISC-V processors. These calls will receive 80 million euros from the EU and its member states. You can expect more such KDT calls in the future. That's on the roadmap. To different degrees, you can find RISC-V and open source hardware in other projects funded by the European Union and the European Space Agency. RISC-V and open source hardware are really gaining momentum in Europe. So it's high time for you to board this train. Some of the Thales activities on CVA6 are supported by the Fractal project funded by the European Union through the Excel joint undertaking, now the KDT joint undertaking. Thanks for the support. As a conclusion, I'm convinced that open source hardware is the next open source revolution. If you're a software developer, you will perhaps encounter RISC-V, OpenHW Group cores, or even CVA6 in a future project. If you are more on the hardware side of the force, really consider CVA6 for your next product. It's mature, it's independent from the FPGA or ASIC technology, and you will get a strong open source ecosystem to support your product. Thank you for attending this presentation. I am handing over to the OpenHW staff to answer your questions. Goodbye.
Can you hear me? Yes. So now it's the time for questions. If you have any, me, Max, and Rick behind you can answer any questions that relates to open hardware or this talk in particular.
Thanks for the presentation. I'm not sure if I understand it correctly, so therefore the question. Can I use one piece of software written for one core, so to speak, on another core? For example, provided from a commercial SoC vendor? Is this a bit compatible, so to speak?
Well, if you can compile it for RISC-V, yes. The core is a RISC-V core. It supports the standard RISC-V with floating point, multiplications, and so on. So if your code compiles with RISC-V, then it should be capable of being executed, yes, unless it depends on platform-specific stuff.
Okay.
As usual, yeah.
Okay, thanks.
You're welcome.
I'm just going to add a little more color to the answer to that question. It's just like ARM, right? If you have an ARM ISA compatible core sitting beside another ARM ISA compatible core, in theory, the binary should execute on both of those cores. The issue is usually not with the core. The issue is with all the peripherals that sit around the core that have different hardware register maps and different features and different functionalities, so you can't take the binaries and just blindly expect them to execute on even if it's the exact same core in an NXP device sitting next to, say, a Qualcomm device, the exact same core. It's the rest of the peripherals all around and the drivers, for those peripherals that will be different. The exact same thing will happen with any RISC-V implementation. The ISA itself is not the issue. Sure, but I don't think I know of any single SoC that's the same from multiple, vendors. Yeah.
Plus, if your application that you have in mind is, let's say, hardware abstraction layers, usually there's assembly behind, somewhere.
Yeah.
And that you have to port it by hand.
So you mentioned there are some extensions possible, like coprocessors. Do you design any of those coprocessors? Do you have any designs for like a vector extension processor, crypto, or like a GPU, which would be nice?
GPU, no, but for the others, yes. Actually, the vector coprocessor is part of OpenHW Group. Is one of the OpenHW Group projects that is run by ATH Zürich and Polytechnique of Montreal. So they are developing the RISC-V standard vector extensions into exactly this CPU. And then there are other plethora of coprocessors in development, both open and closed source, that that relies on the CVX interface. So we have at least 2 cores supporting CVA6 interface in our IP portfolio, and we ourselves are specifying the interface to extend the CPU. What is good about this interface is that it makes the IP agnostic of the interface. So this is not something new. I've often asked, what's new about this interface? Well, technically, when you put all the pieces together, nothing. But if you think about it, the way you can be detached by the core into the database at database level is really nice. I'll explain you in a second. So on GitHub, you find the CPUs, and they expose an interface. Now, usually, the core that are extendable have a coprocessor part with an interface, but then you have to put your hands inside the decoder to say, hey, when the instruction A, B, C, D, F comes, please take this guy and put it outside the interface such that my coprocessors can do my funny logarithmic instruction or whatever. In this case, no. In this case, whatever the core does not recognize, it is sent through the coprocessor. So you just clone the GitHub repository and you never touch it. You don't touch it, so you don't have to fork and maintain your own version. That's why we made it, because we don't want people to maintain their own CPUs. So you can be an open source or a closed source coprocessor developer, and you don't care about the CPU at all. Mm-hmm. Thanks. Any other questions? And thanks a lot.